Hello, everyone. Welcome to episode 1 of the Typechecker podcast.
Hello, Andre. I'm Jonathan Goodwin.
As a brief aside, this episode was recorded in August of 2019, so not everything we discuss will necessarily be up to date at the time you're listening to it. Jon is the primary developer of the programming language Cone.
A few years ago, like everyone, I was playing online video games across the internet, and it occurred to me, why is it that when we're browsing the web, we can't do so in 3D worlds? Everything that we view is two-dimensional pages, images, whatever. And so I thought that I'd play with it and explore it and see if we could do something about that. I started up a language called Acorn that was dynamically typed, intending for it to provide ease of use and flexibility. And after a few years of working on it, I ended up being able to create a simple browser with Acorn embedded that brought in Acorn files from the internet and displayed 3D worlds that you could interact with. But as I was looking at the design and architecture for it, I realized that it wasn't going to scale from a performance standpoint. And so I started to look at how could I accomplish the same things using a statically typed language. C++ is typically considered the gold standard for game development, but I find it to be really inconvenient to use, very verbose with a lot of verbiage needed in order to make simple things happen. And I wanted to see if we could do something better than that. I had also heard around that time of two interesting languages, Rust and Pony, that intrigued me. Rust for its unique memory management model, and Pony for the way that it handled concurrency. Both of them touted lockless capabilities from a concurrency standpoint, and that really interested me. So I took a deeper look into both languages, and as I did so, I realized that there were some similar patterns, but each had some things that the other didn't have. And I wondered, hey, could we bring those two capabilities together into a single architecture? I ended up writing a paper on it called Gradual Memory Management, and that launched me into building Cone based on the principles that I outlined in that paper. My intent was to create a language that allowed one to create 3D worlds that operated across the internet, but took advantage of the kinds of things that video game designers have long known about handling memory in more efficient ways rather than doing a simple memory allocation and tracing garbage collection. Can we use multiple different memory management strategies the way that video game designers often have to create a better performing and a more real-time performance capability?
So it sounds like what you're saying is that in Cone you can use multiple memory management strategies. Would that be correct?
The basic idea is that you have different regions. Each region manages its own memory. So you might have a tracing garbage collection region, you might have a reference counted region, you might have a single owner region, you might have one based on arenas or one based on pools. Each of these different regions manages memory in very different ways. Some give you greater performance, some give you greater data flexibility, some are not so good at real-time performance where others are. So the idea is that you mix and match those region strategies. When you allocate, you specify which region you're allocating out of, and then you get the benefits of that for that particular piece of data.
So I noticed on your website you call Cone a fast, fit, friendly, and safe systems programming language. What causes you to call it a systems programming language as opposed to like a web programming language?
I call it a systems programming language because it really lives in the same category as C, C++, Rust, and D. It gets down to the hardware, particularly with pointer and reference support. So it is a full-scale systems programming language. It just happens that the area that I want to focus its attention on is 3D on the web. You could use it to build network servers, which you'd need for 3D online worlds anyway. You can use it to build browsers. You can use it to build a whole bunch of other things that you would use a systems programming language for.
So I can imagine why you would want to have different memory managed systems or models for different programs. But why would I ever want to have multiple in the same program?
Sure. The single owner region, for instance, which is what Rust is known for and which Cyclone helped pioneer, is particularly good when you want determinism. You want the ability to say, here, let me allocate this data object, and I only want one reference to it ever. The owner holds on to that. You can make use of it as long as you want, and then when you no longer need it, it's gone. There's no overhead associated with that. From a runtime management perspective, the compiler is able to figure out exactly when to get rid of it. So you've got a performance characteristic with that. But the problem with the single owner model is the data structures that it can support. It needs a hierarchical data structure at the most. It isn't going to handle a complex cyclic kind of data structure where references are pointing at one another all the time. For that, you're going to need something that isn't going to perform as well, like reference counting or tracing, but will give you the flexibility to manage those data structures effectively and safely. Arenas are particularly good because they're going to be incredibly fast. The problem is that they leak memory. You can't always get rid of things as fast as maybe you'd like because the whole arena goes away at one time. You get the speed advantage of it, but you have to be careful about not running out of memory.
Why would an arena be faster than Rust's model?
The fact that it makes use of a very, very simple memory allocation mechanism, a bump pointer. When you want a new piece of memory out of an arena, it's very, very, very simple operation. It happens extremely quickly. A lot of the modern tracing garbage collection strategies make use of an arena in the new generation of data, but then you have all the extra overhead that's associated with the tracing garbage collection. So an arena is really that pure new generation, very, very, very fast allocation, very fast free because the whole arena gets freed at once. You're not individually freeing each of the segments as you go along. So basically, if you want speed, you're going to want arenas. You might want a single owner. You probably will want pools. Those are going to give you the best performance, but they've got some really severe downsides. And for certain data structures, you're going to need more flexibility, and that's where things like reference counting and tracing garbage collection are going to come into play. So you need the flexibility of being able to go as fast as possible where the data structures permit it, but then you want the flexibility to be able to fall back on some somewhat slower mechanisms. The nice thing is you're not having every data structure using the slowest techniques. You're only having those data structures that really require it, making use of them.
So, how does this all fit in with concurrency?
Sure. And a lot of this comes from Pony, particularly, which is the idea of being able to have lockless safety mechanisms. And you see this as well with Rust in terms of its single owner model, that you can have a mutable piece of data that you can move from thread to thread to thread, and there's no locks involved in that. So the basic idea in Cone is to leverage the fact that historically we've always used locks, and locks definitely have their place. Synchronization mechanisms have their place in building multi-threaded programs. But we have these other mechanisms that have been developed over the last couple of decades that are really flexible and interesting, and they take the load off of the performance sapping nature of locks. Things like the single owner, single reference linear systems that allow you to move mutable data around. It is also possible within a single thread to have shared mutable. So what the permissions do in Cone is to give you for each reference the ability to say, here's which race safety mechanism or strategy that I want to use for this. In this particular case, I want it to be single owner, and I can move that mutable data from thread to thread, but I can only have one reference to it. In this case, I want the data to only stay inside a thread, but I can have shared mutable references to it. In another case, I have data, I've created it mutably, I'm done, I lock it, I freeze it as immutable, and now I can share it across all of my threads. All of those strategies are lockless. But in addition, you also want the ability to be able to say, well, I want this data to be shared across threads. I want it to be mutable. And then I'm going to make use of these synchronization mechanisms to keep it safe from race issues. So the idea with race safety in Cone is similar to the idea of memory safety in Cone, that you have multiple different strategies for accomplishing race safety, and you as the programmer get to pick which one applies best to the data that you're working with.
So here's something that's just occurred to me. When I write a function, can I write it in such a way that it will work with any value, no matter what type of memory management it's using?
Yeah, that's an interesting question. And the answer is yes. If you look at all the different regions, there's actually another that I hadn't mentioned, but if you're familiar with Rust, you know about it, and that's the idea of a borrowed reference. So the idea is that any reference that's been created through a region, you can then borrow that reference for some piece of function scope and work with it in this borrowed state that really is polymorphic to the original region's reference. So you can write functions that work with data without any knowledge or regard for what region actually allocated the data. You can work with the data and bring information back. And so it's polymorphic in that sense. And similarly, with regard to permissions that we spoke about earlier, all of the permissions basically can be coerced into a const permission that says I can look at the data, but I can't mutate it. And so in both cases, you're able to collapse your strategies into a very simple version of it that allows you to do a tremendous amount of work without needing a lot of different versions of the same function.
So a borrowed reference and an immutable permission that's maximally restrictive?
That's correct.
Okay, I think that's about all the questions I have. Thank you so much for coming on, Jon. And I know there's a WebAssembly demo of Cone on your website, if you want to shout that out.
It's cone.jondgoodwin, Jond is in David, Goodwin.com. And that provides a playground so people can play with it at its current level of implementation. It's got a long ways to go, probably several years before I'm ready to release it as something that people can use. But you certainly can learn a lot of it. My current focus right now is to finish up the documentation, the reference for it, so everyone, especially me, knows exactly what the language is going to look like that as it gets implemented.
And thank you so much for coming. And for everyone listening, I also really recommend you check out his website, not just for the Cone demo, but also because he has a really stellar blog. It comes up if you just Google Cone language. So I'd really recommend you check it out. And thank you so much for listening. I think that's a wrap.